section 5.4 is on page 383. Talks about work. This is a really straightforward section. If you've taken general physics, this should be a breeze. And if not, here it is. That's not a big deal. We start with, we want to know how much work is required to move a specific object a certain distance. So we need to know a few things. We need to know the force. And force is ma. And m is the mass. That's normally in kilograms. And a is the acceleration. It has really two units. It could be in meters per second squared or feet per second squared, depending on the problem. And if I take the acceleration and write it as the second derivative of s, where s is the position of a particle with respect to time, the units would become kilograms times meters per second squared. Now, really quick. Due to gravity, if the only force working on an object is free fall, just gravity, F equal mg. M is the mass. Again, that's normally in kilograms. This you have two options. It's either 9.8 meters per second squared, or it is 32 feet per second squared. And if you use 10 before, you should start using 9.8 instead. And of course, this is gravity. Alright, so that's a quick review of what force is. If you didn't know that, here it is. Now we talk about work, and it's the same work as we defined in physics. It's really force times distance. Now, if the force is constant, I really don't need calculus. So we say work equal force. Normally force is in newtons. If you take kilograms times meters per second squared, that's newtons. And I don't want to put an X, you might think it's the cross product, times distance. Distance normally is in meters. And if you take newtons and multiply them by meters, that gives you joules, right? Which normally are kilograms meters squared per second squared. Now, to match the back of the book, you really should work out those units. Force normally is in newtons, which is kilograms meters per second squared, and work is normally joules. That is newtons times meters, or kilograms times meters squared per second squared. So to match the back of the book, I should really convert all of those. And let me see if I still have that. I saved something. There it is. Now, if the force is fixed, this is really simple to do. Just take the force times the distance and we're done. But if the force is varying, that is, if I wanted to push a car, I don't know if you guys have done that, but in my days we used to do that a lot. If you push a car, it seems to be very hard just to get the car moving. Once it moves, you'll notice it's easier to push it. I'm not saying go out there and push a car, but that's how it is. If you want to push a big box, it's very hard to get the box to move. Once the box starts moving on the floor, you'll notice it's easier. You don't need as much force to move it. So, if the force is fixed, if you have an engine that's given out a certain amount of, whatever, kilograms or horsepower, or, then that's fixed. But if you are doing the work in which the force is varying, you need integration, because that's the force that's varying over certain intervals, and the work is varying from point to point. If I'm pushing a car, the force is going to be a lot bigger than once the car keeps on moving. So you'll notice I'll have a hard time getting the car moving. Once it moves, I could probably push it with one hand, because the car now is helping. I'm not going to get into the physics theory and first law and second law and any of that. So basically, if we have a varying force, we're going to integrate from A to B. F is the force, and dx is the actual direction in x. We're going to use this mainly for Hooke's law, and let me elaborate really quick. if I look at, and that's the main use here, I could use it for some more, but applications, we're not going to get into that. If I take a spring and I let it rest, wherever it rests, I assume that's 0. So this is spring at rest. Basically, you take the spring and you let the system go. Don't touch it. Don't add any additional influences to it. Wherever it stops, assume that's 0. Now you could either compress this or stretch it. We're going to say X would be the actual stretch beyond. So this is the stretch or compression. So stretch / compress beyond its natural length. Okay, so keep that in mind when we look at this. And Hooke's law works at Hooke's law states that the force is K times X. This would be the force. K is the spring constant that varies from spring to spring. You have to find that every time. And X is the actual distance, stretch or compress. Oh boy. Stretch or compress. So, I want to start with problem number 2. I would have did number 4 and 6, but they have an exception that doesn't come up on the homework. And again, I just want to introduce this. You will really touch on this heavily in the 3rd semester calculus. So for now, they're saying how much work is done when a hoist lifts a 200 kilogram rock to a height of 3 meters. Work equals force times distance. Well, the force in this case, the only thing working against this when it says lifts up, the only thing that's working on the force is actually gravity. And what's gravity in this case? This is MA. M is 200 kilograms, and since this is in meters, times 9.8 meters per second squared. So the units here give automatically newtons. That would be 200 times 9.8, and the units are newtons, times distance. And the distance is 3 meters. And if I multiply those all together, what do I get? That would be a total of, now I could plug this in my calculator and figure out that this, well, actually you could leave it like that, that's not a big deal. So 3600 times 9.8, and the units altogether would be in joules. So this problem, the force is not varying. The only thing working against it is really gravity, and that's really a straightforward problem. But if I look at number 8, I notice that we have a spring right, and we're gonna assume, now some assume halfway is 0. It really doesn't matter as long as you label it to be a point. Let's say right there is 0, so you let it rest. A spring has a natural length of 40 centimeters. This is 40 centimeters. A 60 force newtons, so the force is 60 newtons, is required to keep the spring compressed 10 centimeters. X is 10 centimeters. That would be 0.10 meters. Alright, well, the first thing that I need to do on every problem is take f of x according to Hooke's law and figure out how stiff is this system? Well, they gave me the force. The force is 60. K is what I'm looking for. And the 60 newtons force compressed at 0.10. So K is 60 divided by 0.10. That is actually 600. Now, you could write newtons per meters, but I'm gonna really be picky about the units at the end of the problem, not as you carry the problem. So, now that I have this, I know that f of x is actually, so the force for the system is actually 600x. There it is. Now what? Well, this force is going to vary. Keep in mind, if I compress the spring 10 centimeters, the next 10 centimeters will take a lot more force. As the system gets compressed, it's going to be harder to pull this in. Same thing if you stretch it. If you take a spring and stretch it 10 centimeters, the first centimeters will require less force than the next 10 centimeters because now you're really approaching the break point of the resistance in which the system might break. If I look at what they're asking me to do, they're asking for how much work is done by this compression. Well, let's see. The work done by this compression, 0 to 0.10 of 600x dx. There it is. Once you get the force, you're set. That's 300x squared evaluated from 0 to 0.10. That is 300 times 0.10 squared. I worked this out already. That turns out to be 3. And the units are in joules since this was matching in newtons per meters, or this is in newtons and we converted that to meters. We're in a very good shape. And then they ask another question. They say, all right, now, how much work is required to compress this spring 25 centimeters? Well, the work required is going to be the integral from 0 to 0.25 of 600x dx. And the work will be 300x squared evaluated from 0 to 0.25. Well, guess what? It turns out that is fixed. You'll get that every time for this specific system. And this is going to be 300 times 0.25 squared. Again, I cheated. I used my calculator. I really don't mind you leaving the answer like that on the final or the exam, as long as you write me the units. Me and you are very happy. Right, let me set up the next problem. So, number 10, if the work required to stretch a spring 1 foot, the work required to stretch a spring 1 foot beyond its natural length, and we know that f of x in this case is kx, so this is the integral 0 to 1 of kx dx. The work required is 12 feet. Again, you really don't have to drag this, you can do this at the end. What's my first order of business? I need to find k. So doesn't this say kx squared over 2 evaluated from 0 to 1 equal 12? Or I could say k times 1/2 equal 12. That means k is 24. So I know for this specific system, for this spring, f of x is actually 24x. Got it. I need to get k every time. How much work is needed to stretch the spring 9 inches work? So again, if this is in feet, if I take 9 inches to feet, each one of those is 12 of those, that's 3/4. So 0 to 3/4, right, of 24x dx. That is 12x squared evaluated from 0 to 3/4. That is 12 times 9 over 16. Again, I really don't mind you leaving the answer like that on a test, right? Again, that turns out to be 6.75, but I need the units at the end. And that's all there is for this section. Let me give you the homework. And the homework on this section is page 371, number 3 through 11.